Bienvenue au séminaire de 2021. C'est professeur Tadahiro Taniguchi, qui est professeur d'intelligence humaine et informatique à l'université de Résumé à Kyoto, chercheur en chef général invité à la division de technologie de Panasonic en plus. Ses recherches portent sur l'intelligence artificielle, l'émergence de symboles en robotique, l'apprentissage automatique et les sciences cognitives. Il a été dernièrement à Montréal à l'UQAM en 2015 et il collabore avec professeur Angelo Cangelosi de l'Université de Manchester, qui a déjà assisté dans cette série de séminaires et qui sera, j'espère, un de nos conférenciers l'année prochaine. Professeur Taniguchi a aussi collaboré à la traduction du livre de professeur Cangelosi. Tadahiro Taniguchi is a professor of human and computer intelligence at Ritsumeikan University in Kyoto. He is also visiting general chief scientist in the technical division of Panasonic, and his research is on artificial intelligence, symbol emergence, in robotics, machine learning, and cognitive science. He spoke in Montreal at UQAM in 2015 and has collaborated with Angelo Cangelosi of University of Manchester and collaborated in the translation of his book. I hope Professor Cangelosi will be in our series next year. And now I welcome Professor Taniguchi, who will be speaking. And if you have questions, you should put them in the chat and I will discreetly inform Professor Taniguchi, and he will decide whether that question should be answered right away or should be deferred until later for the question period. Welcome, Professor Taniguchi. Bienvenue.
Okay. Thank you very much. Thank you very much for introducing me. Thank you very much for inviting me as a speaker. So I'm Tadahiro Taniguchi from Ritsumeikan University. And it's my great honor to be given this opportunity to present this talk in this online seminar. So today, I'll be talking about symbol emergence in robotics, probabilistic generative models for real-world multimodal language acquisition and understanding. If you have any question, please don't hesitate to ask via chat, okay? So maybe my pronunciation is too Japanese, so if you cannot catch what I said, please don't hesitate to ask or check, confirm as well. So this is my brief introduction of myself. So I'm working as a professor for College of Information Science and Engineering at Ritsumeikan University, which is located nearby Kyoto in Japan. So I'm also working for Panasonic as well. Panasonic is a home appliance company. Okay, they are now investing so much to AI as well. Okay, so let's move on to the topic of this talk. Okay, sorry. Okay. So we researchers in developmental and cognitive robotics are interested in the computational understanding of human mental development. So actually, you know, a human child acquires so many physical skills, concept, and knowledge, including language, through physical and social interaction with their environment. So, and just from their own experiences, from this viewpoint, from the viewpoint of AI and robotics researchers, the learning capability of children is incredible. You know? We would like to obtain an understanding of computational process of mental development and especially language acquisition. So it is essential to develop computational and robotic models that can reproduce such process. So first, let me show you some videos to give some flavors of our studies. How can we make a robot more cognitive and developmental based on its sensory motor experiences is a central question in cognitive and developmental robotics.
Tadahiro,
Yeah.
just let me ask you, did you want to already share your screen? Because it's not sharing now.
Already, sorry, super sorry.
That's all right.
It's fatal error. Can you see my slide?
Yes, now that's fine.
Wow, too bad. Sorry. So this is a previous slide, and this is my previous slide. Okay, sorry for that. So, okay. Anyway, please watch this video. Maybe there's no big problem. Okay. So this is the movie I wanted to show. So in this case, in this sense, of course, this field shares many challenges with AI and robotics community. So I will explain the detail of some of this video as the later part of this lecture. Okay, so before start talking about the simple emergence in robotics and developmental robotics, let me explain the kind of the broad sense of the AI. So of course, many of you may know that recently, during this decade, artificial intelligence made huge success in many tasks. No, so for example, AlphaGo beat the human Go champion, and self-driving car run autonomously, and many kinds of elemental theories contributed to success. So, please let me revisit the fundamental question: what's AI and what's current AI technology? First, I'd like to give a very brief introduction of the current notion of the AI, the many parts of AI current. So in the current hype of AI, intelligence tend to be regarded as a function or mapping. So for example, the visual recognition system receive image data, and it map the image data to label data. This is image recognition, and automatic speech recognition system takes speech signal, and it map the speech signals to the transcribed data, transcription. And for example, machine translation system take, for example, English text and map it to the Japanese text or French text, for example. So this kind of the function type of view that can explain many parts of the current AI technologies. Then actually deep learning arrived, and by using the deep learning architecture and by optimizing the future parameters of deep neural networks, we can create some sort of the pattern processing function. So this type of machine learning approach is often called end-to-end learning. So because it can optimize from an end to another end. Okay. Then later, of course, the more complex functions have been explored and developed. So we can in this but we can ask this question. So is this a natural process of our cognitive development, or is intelligence just a function? So they can be regarded as a function to some extent. But I think we need to reframe the notion of intelligence or cognitive system to further development of AI. So, so actually, our society made a huge progress in AI. But AI, from this viewpoint, AI technologies, AI society is still regarding as an intelligence as a single function, single purpose function, and very task-oriented. And it can be said the intelligence as a procedure and no autonomy. But when we look at our children, so they are not, their intelligence is not for single task-oriented. And actually, the developmental process is some sort of the self-organization of the sensory information flow, and they have autonomy. So this kind of idea that is echoing the predictive coding and the free energy principle proposed by Carl Friston, for example. So, and actually such a bottom-up self-organizational learning process, result to not only acquisition of physical skill, but also the linguistic skill, language acquisition as well. So, okay. So one of the main goal of this talk is to introduce a simple emergence in robotics. Here, I'd like to give a flavor of a research of our here. So it is a bit old research conducted about almost 10 years ago. A robot moves around and grabs the object several times to obtain the haptic information, and it obtained it shakes the object and to get auditory information, and looks at the object to obtain visual information. So the robot obtained multimodal information, the haptic, the visual, and auditory information. So after that, the robot uses the unsupervised learning method to integrate the multimodal sensory information, the multimodal latent Dirichlet allocation. This is a kind of the multimodal unsupervised machine learning method that was used for the unsupervised object categorization, the task. Okay. So I skipped the detail of the method, but this is an example of the categorization result. The categorization results shows the robot could obtain, that could form some sorts of categories very similar to the most of the human participants. The wizard, yeah.
Could I ask a question? And it's a good time for a pause. Is this still unsupervised learning?
Yes, basically, from the viewpoint, in machine learning terminology, by using just the input or sensor information is just a haptic and visual and auditory information. There is no supervision. Yeah.
And what is the demonstration that they have got the category? I mean, normally we think that to get a category, you have to be able to do trial and error and get feedback on whether you're right or wrong. But in unsupervised learning, you don't have that. So how do you know they have a category?
Oh, that's a good question. And basically, we gave label here, but it's not given to the robot, and this is given. These are given by the how to say human translator, human interpreter later. Basically the robot can form. How to say the robot have here. Robot have latent variables. So for each, please see this is a kind of image. So in this learning system, the robot have several latent variables. So some observations is allocated to one variable. So how to say, by looking at the variable, we can interpret that a robot, this robot regards this object and this object are same, something like that.
Can I just pursue just a little bit more so I know what you mean by we know that it regarded as the same? What it has been receiving is input without labels, without reinforcement, without feedback. And whatever it learns, even using its latent variables, whatever it learns is based on the distributional and correlational structure of its input.
That's
is
right.
That correct?
That's right.
And
That's
on the basis of that, what is there in the input to show that it's doing categorization according to your labeling?
You mean what is the actual input of the sensor information? You mean?
It's more what where in the output do you draw the conclusion that the system is categorizing in this way according to these labels? You point to the latent variables, but that's just part of the correlational structure.
That's right. That's right.
And I'm asking how it comes out in the output of what I mean. Your robots that you showed were actually doing things, right, with objects.
Yeah.
How does this translate into what it does in the world?
What it does in the world.
How does this kind of learning turn into or develop into what the robot can do in the world? Because in the world, we can categorize stuffed animals. We do something different with stuffed animals and something different with toy vegetables and something different with
Okay. You mean how the robot can use this kind of category?
Yes.
Okay. So this research is somehow at the preliminary stage. So in this experiment, what robot could do is just finding a kind of the correlational structure, and how to say, so the robot can differentiate this object and this object are different, or this object and this object are similar, or that's what the robot could do. And maybe so that it's still a bit far from the human categorization.
Because categorization is not similarity judgment. You're talking about similarity judgment. I can see clearly how correlations would lead to the ability to say this is more similar to that than to that. But I don't see so clearly how it tells a robot you can do this with this and you can do that with that.
Related to actions?
Yes. And that's why I asked if there was any supervised learning or reinforcement learning, or still just unsupervised learning.
Basically, this example, this kind of movement, actually implemented. So this kind of behavior is not trained. So I'll say we introduce some sort of a trick about the behavior. So so I know that's the kind of limitation of this work. So can I continue?
You can always continue, of course. Thank you very much.
Okay. So, okay. So let me move on. That's the kind of the study that 10 years ago, conducted 10 years ago. So that I want to gradually move forward. So let me move on to the language acquisition problem. So the similar problem that can be found in the speech recognition system and the speech synthesis system. For example, in the very ordinary approach of artificial intelligence, when we develop the speech recognition system, we prepare the bunch of speech signals and transcribe data. And if you train the speech recognition system using this kind of pair that you can train the speech recognition system. And the speech synthesis system is also trained by creating the function that can map that maps transcription to speech signals. But when we look at our children, there is no transcription data before he or she become able to speak or understand a language. So, children that take speech signals and found some structure inside of their brain and produce the utterances. Okay, so without any transcribed data. So this is a huge difference between the current AI and human language acquisition. So considering the language development of infants, let me take an example called word discovery. So in language acquisition, word discovery or word segmentation is a critical task for infant. When parents speak to their children, they rarely use isolated words, but use continuous word sequence. So therefore, word segmentation is a primary task of language acquisition by children. So they have to perform word segmentation without pre-existing knowledge of vocabulary and even phonetic system, because children do not know lists of words and phonemes before they learn. They don't have access to transcription as well. So then what kind of assumption can we use for speech signals to perform unsupervised word discovery? So in our research, we focused on double articulation structure. This is very simple structure. And actually, every language all over the world have this kind of double articulation structure. So the speech signal is basically continuous and high-dimensional time series data. And the spoken sentences is considered as a sequence of phonemes. The phonemes are groups into words, and the people tend to give them meanings. This kind of two-layer hierarchy is very general. And based on this kind of very, very basic assumption, we proposed the hierarchical, the Bayesian model. We developed the probabilistic general model for time series data having double articulation structure that is assumed to be embedded in every language all over the world. So this is a graphical model, but this might look very complicated, but the idea is very simple. So this is just a probabilistic model. So this L means sequence of phoneme, and this Z means a sequence of words. So there is a two-layer hierarchy, and okay, and by using Bayesian inference, the system can infer all of the latent variables, the word sequence, phoneme sequence, the list of phonemes, and the list of words from speech signals. So this is the illustrative figure of the target problem and our approach. The robot, the system takes continuous speech signals and acoustic model. This is a kind of the phoneme, the knowledge of phonemes, and language model. This is a kind of the knowledge of words. Both of them are estimated, inferred from the speech signal. Okay, so let me skip the detail of the result, but we showed that our method, this method, can find the words and the phoneme just from the sensor signals. speech signals. And this, how to say, for some simple data set that was competitive to the current or very conventional the speech recognition system. But you know, the finding words and phoneme from speech signal alone is still challenging a problem. And I don't think the language acquisition just from speech signal that is not so reasonable one. So so we go further. We went further. So actually the developmental psychologists said the children use several kinds of cues for performing the word discovery. There are 3 representatives: the prosodic cues, distributional cues, and the co-occurrence cues. Here, let's focus on the co-occurrence cues. So to detect, when a person talks to a robot showing an apple, for example, the probability that the sentence contains a word about apple will be high. So if a robot can make use of such information, co-occurrence cues, the performance of word segmentation or word discovery will increase. So however, to detect the co-occurrence of an object and the phrase, the robot has to form the category of the object beforehand or simultaneously. How can a robot form object category without knowing the names of object? So because the robot is now performing the word discovery. So one of the solutions is multimodal object categorization that I introduced in the previous talk. So this is a kind of the picture about the simultaneous acquisition of words unit, the multimodal object categories. You know, this is the image captured from the previous video, and we proposed this kind of graphical model that looks complicated as well. But basically, we combined the multimodal categorization, the method, and the word discovery system, speech recognition method. So, and the object categorization system and the speech recognition system, the word discovery system are trained, optimized at the same time in an iterative manner. Okay. So okay. So this slide gives us an overview of the experiment, showing some image showing some the experimental condition and result. So and it shows that both object categorization and the speech recognition, the performance improved using the co-occurrence cues. Yeah, actually, by using the object category information, the word discovery performance is improved. And actually, if proper words can be found, such kind of information can be used for multimodal categorization as well. So that they help each other. Okay, this is another the work of us. And later, they actually what's important for the robot that live together with us and provide services to us is not just the object category and the lexical knowledge. For example, in the service environment, please go to the kitchen. If we ask a robot, please go to the kitchen and bring me a bottle or something like that, such kind of command is very popular. And you can find that not only object, but also place name that is uttered, that is spoken by the users. So some sort of place category or knowledge of spaces are very important. So we to tackle this problem, we developed the machine learning method called SPCO-SLAM. This is a kind of online spatial concept acquisition method. So this method can form, map, and find the clusters of positions and discover words representing places from speech signals simultaneously by integrating multimodal information. So actually, when we think about what's the kitchen, for example, for the robot or for us. So in ordinary approach of robotics, the robot that recognize its position as a kind of XY coordinate. So the kitchen will be some part on the map. But for us, when we visit my friend's home, we can easily find, oh, it's a kitchen or kitchen is there. So because there is a refrigerator and there is a microwave and so on. Such kind of visual information or some human's behavior that can tell us where is the kitchen. And so actually this tells us the place knowledge or place concept is also based on multimodal information. So this is again some sort of the diagram of this model. So the SPCO-SLAM estimates the map and robot self-location, and at the same time, the robot forms a cluster of a category of the positions and the find words as well. So this is again a bit complicated model, but let me explain briefly that this part, the upper part representing the graphical model, generative model for SLAM, the mapping and localization, and this part, the red part, is representing some clustering method for positions. And the blue part is representing the image recognition system. And this part is a speech recognition system, including word discovery. So these cognitive modules are integrated through this integrative generative model, probabilistic generative model. And this is a video of experiment. So the robot move around in the building, and time to time, a person is talked to the robot, or you are walking on the corridor, or you are visiting the toilet, or you are now in the copy room, and so on. So by receiving this kind of speech signals, the robot finds words without any pre-existing the linguistic knowledge, the lexical knowledge. And at the same time, the robot form this kind of maps and estimate its position and find the cluster of the position by integrating the image information and such kind of the linguistic information and positional information. So, and I know that this is just a clustering of the multimodal information, but this I think that this will be able to be used for further the tasks. Okay, but interestingly, so while we are conducting this kind of research, we face the problem. So actually we want to introduce this kind of technology to the service robot, like a automatic vacuum cleaner and so on. So, but when robots become so adaptive and learnable and become able to obtain new knowledge automatically, we face the new problem. from the viewpoint of human-robot interaction. So in service robots. So it becomes hard for us to know what the robot is recognizing and what the robot is planning and so on. To tackle this problem, we introduced a mixed reality technology recently. Okay. So this is not about the study of developmental robotics, but sorry for the Japanese text. But this shows by using the AR, mixed reality device, so what robot is thinking can be shown on the real world environment virtually. Okay. So now the user can see, robot considers here kitchen, and the robot is recognizing this is a sofa and so on. So if we can understand the robot's recognition state in this way, that will help the human-robot interaction. Okay. So this is a video. This kind of system was also introduced to the robotic convection environment. Oh, sorry. I'm sorry for stopping. And actually, in my side, the very loud sound was happening. Sorry. And so as a showcase, we implemented some of our technologies to this kind of robotics competition. This is a World Robot Summit 2018. Actually, the World Robot Summit is a kind of robot Olympic that planned, organized by Japanese government. And actually, the World Robot Summit should have been organized last year, 2020, along with Tokyo Olympic. But unfortunately, that was extended that was postponed because of the COVID-19. So then actually we got the first prize in this event. Okay, so this was just application. So I have the 10 more minutes, 5 more minutes. Okay, so okay, so let's revisit this model. Okay, so okay, by developing this kind of the integrative.
Can I make a suggestion? This would be an excellent time for me to ask if there are people that have burning questions in order to be able to understand what's going on now.
Okay.
Okay. So could you, if you have a question to ask, turn on your microphone and speak aloud, because
wow,
it's
so many questions, Kevin.
You don't have to read them. I'll ask the
okay.
I'll ask the person who wants to ask the question to say it out loud slowly, because they're explaining to people who speak 2 other languages.
Okay, so please. Yeah.
For example, Tufik, do you want to say something?
Non, merci. C'était juste un commentaire par rapport à votre intervention. Merci.
D'accord, c'est bon. Pierre, do you have something to say? Pierre?
Yes, I'm there.
Okay. But make it short, because this is just a pause. Go ahead.
Okay. The thing is really what is required before you can start training your robot. What do you have to load into your system? In other words, I will call this what is innate into your robot. Like you use phonemes for the speech elements. How And I find this already a major improvement over using words, because phonemes don't have any semantic load. But still, it has to be parsed by the system before you can use the phonemes into your robot. So what do you have to load into your system to separate the phonemes like this from the other sounds? Like there's all kinds of sounds outside. How do you load it in there? Because this is already some semantic.
Okay.
I also have questions about depth or distance. For the mapping, the robot has to move from one place to another to discover the distance between where it was and where it is now. But that distance, how do you translate it into a world model? Because it's at the beginning, it's only a robot who is aware of that. It is only aware of that distance. And how do you put this together into the mapping?
Okay.
Very great.
Very great.
Yeah, that's fine. But let Tadahiro answer now, and we'll go to questions much later. Go ahead, Tadahiro.
Can I?
Yes.
Yeah, thank you for the great question. And you take a very nice point, great point. And actually, for example, this system, I said that this system could find the phoneme and the words simultaneously. So, but actually this, and when we tested this system, we just put the human speech signals separatedly from the other environmental sound. So that's a start point. And actually the human children that should distinguish the human voice, human speech from environmental signals. And if we put the environmental signals to this system at the same time, the system cannot work. So that's of course, we still have such kind of challenge. And in addition, but what we give to this system is not a phoneme sequence, but kind of the the sequence. So there are many kinds of phonemes but this system can automatically find the cluster of sound, and I mean the phoneme. Okay, so the number of phonemes are also estimated automatically, basically. And about this mapping, yes. So you are taking a very good point. Actually, the robot can form this kind of map. This system is basically based on SLAM. The SLAM is very standard approach in robotics for mapping, but this method this method uses the odometry information. That is a kind of the forward model or sensor, the interpretation of the sensor signal as well. So such kind of very, the pre-existing knowledge of the objective coordinate is given. So from the viewpoint of human development, it's not reasonable. Actually, I want to throw away such kind of assumptions. So actually, recently, during this 2 or 3 or 4 years, so the people in machine learning community and deep learning community is looking at world model. The world model approach does not assume such kind of odometry information for building environmental model. So we are very much interested in such kind of approach. We are now moving to such kind of approach as well. Is it?
Yes, that's a very good. It's a very good answer, and you can go on now. If it comes up again, it'll come in at the end.
Okay. Thank you. So the later part is about cognitive, multimodal and cognitive architecture. And okay, maybe time is okay.
Don't worry about the time because you're don't worry about the time because you're mixing your talk and the questions and the questions.
Great. So maybe that you got some sort of flavor or tendency of our approach now. So actually we have been developing this kind of about the complex system, not only a single function, but also the kind of combined integrated system. So this is just an example. In addition to this, we developed this kind of hierarchical multimodal categorization system, and this is a place concept formation method, and this is the simultaneous word discovery and object categorization. So when we look at these models in detail, so we found that most of them are just a kind of the integration, combination of the kind of elemental cognitive modules represented by the probabilistic generative model. That is for the unsupervised learning. But this is a combination of three MLDA modules, and this is just a combination of the speech recognition system, including the word discovery, and MLDA, multimodal categorization. And this model is a combination of SLAM and the Gaussian mixture model and MLDA and the speech recognition system. But all of them are integrated into a single learning system. So, but till now, before this paper, so our colleagues and our collaborators that built this kind of integrative system one by one. So it's very, costly. So after noticing this point, we developed a new framework for developing this kind of integrative model. Okay, so actually, these are graphical model, and these graphical models can be combined via single node. And if we can, then actually we developed a way to combine the different graphical model. And if you open the basic text of machine learning, many textbooks show that there are three types of connections in graphical model, the generative models. And we prepared three ways of communication method between the two modules. So by following this protocol, the two separated modules can be optimized, can learn simultaneously in the same way as the integrated model. So this can help us, and this can accelerate our development of this kind of the integrative cognitive system. We call this approach Serketo. Yeah. Okay, so this is just an example, my toy example. And this is an integrative graphical model, probabilistic model. The task is a simultaneous categorization of the speech signal representing numbers and image of numbers. So, but the point is that there are four very heterogeneous modules. We have very heterogeneous modules: the Gaussian mixture model, variational autoencoder, and latent Dirichlet allocation. This is for clustering, and automatic speech recognition systems. So but we can let them work and learn together by using this framework, circuit framework. So we showed that when we train the VAE, GMM, LDA, ASR one by one, the performance is very limited, clustering performance. But if we connect them and learn together, the clustering performance was improved. So this kind of like integration of cognitive modules and how to say, let them learn together, it's very important, I think. So lastly, finally, I am now approaching to the conclusion, but somebody asked me, why are you so focusing on the probabilistic graphical generative model? So that's a nice, good question. So from machine learning viewpoint, modeling cognitive system with probabilistic generative models and their inference, is a very general view. Actually, from the viewpoint of the probabilistic model, what supervised learning is doing is to model the posterior distribution, conditioned by the observation, Py given X. And unsupervised learning, especially multimodal unsupervised learning, is modeling the joint distribution over several variables, X and P, X and Y. And if we have this joint distribution, actually the Py given X, the posterior distribution can be calculated if it satisfies some conditions. Okay, and so how about reinforcement learning? Actually, there is recently the reinforcement learning is also regarded as probabilistic modeling and inference. So it becomes widely known that reinforcement learning can be reformulated as an inference on probabilistic graphical models. This concept is controlled as probabilistic inference. So Sergey Levine wrote a nice tutorial paper about this. And so this is very nice for us. Actually, this is a graphical model as SLAM again. So the reinforcement learning, the planning can be reinterpreted as an inference on the probabilistic generative model. Then actually this kind of idea give us further, further development of the planning method for spatial concept formation. Sorry. And actually, for example, the robot, after obtaining the spatial concept, so-called spatial concept, the robot can understand, for example, where is the toilet. If the robot hears the sound of the toilet, the robot can infer the position of the toilet as a posterior distribution. And by using such kind of information, the robot can infer the path to the toilet just through the Bayesian inference on this probabilistic generative model. And such kind of inference is mathematically same as the reinforcement learning. That's a very important point. And actually, what I want to say is these ideas can be can be represented on the generative model.
Can I put the question?
Yeah.
I have a problem with this assumption that reinforcement learning can be reformulated as a probabilistic inference system.
Mm-hmm.
The problem is that probabilities usually deal with means, and reinforcement learning aims to acquire expertise. So how do you distinguish between the two? I mean, how can you get precise behavior out of a probabilistic approach?
Maybe I couldn't get the point, or I couldn't catch or.
Oh, that's fine. Okay. Just go on.
You mean the probabilistic modeling is how to say?
Yeah, that would provide decisions, inferences that are true on average.
Okay. Maybe I could get
precisely on specific.
Okay. Maybe I could get your point. Okay. So the basically that's a very interesting point. This tutorial paper, that will give you a very nice introduction to that. Actually, when we formalize the reinforcement learning as inference, as a probabilistic inference, it's called control as inference. We need to introduce an additional variable. It's called optimality variable. So what's this approach? What this approach does is to infer the future trajectory or future control signal. So under the condition that the future, the optimality variable, that means that the behavior is optimal, is observed. So that, how to say?
Okay, I get you.
So that
basically, you're turning the problem into an optimization one. That's fine.
That's right. Yeah. So the point is that inference is very much related to optimization. So the optimization can be reinterpreted as an inference.
Okay, that's fine.
That's the point. Okay. So these are maybe almost time is up. So that's almost all for today. Finally, let me introduce some survey papers. We are researchers in cognitive science, developmental robotics, and neuroscientists. The cognitively wrote a paper about the simple emergence in cognitive systems. And today, my title involves the language, but I think I didn't talk so much about the language. But studying language from the viewpoint of robot is very important. Actually, robot is embodied systems behaving in this world. So actually, natural language processing people tend to look at the text information only. So that extending such kind of idea and the language studying the language in daily use with physical and social system is very important. So we wrote a paper about the challenges in the language and robotics, surveying frontiers of language and robotics as well. So I talked about the kind of integrative cognitive systems. Yes, our brain system is integrating so many the modalities and functions. So another another approach is to develop such kind of integrative cognitive system, learning the human brain structure. So it's also another challenge. We actually published the preprint that on Monday or Tuesday this week, with the collaboration of the neuroscience people. Yeah, so that's another advertisement as well. So that's all for today. So yeah, I welcome the questions. Thank you very much.
Okay, can I suggest that you could stop sharing so that we can see people's faces? But if you need to reply with your PowerPoints, then you can turn it on again.
Yeah.
Okay, so it's open now for a question. And as usual, if there's an embarrassed silence, I can start. All right, so, but please, I want everyone to participate. I don't want to be the one that's doing this.
Yeah.
It's very interesting to see the way that your work has evolved in the last 6 years. If I remember correctly, the same question came up in 2015, which is why so much emphasis on unsupervised learning?
Yeah.
And what really do you mean by symbol emergence? Since the question with symbols is symbol grounding rather than emergence of symbols. Symbols are just arbitrary objects and states. Now, I think I understand one of the developments. It was, as you explained it now, and I think Munir, you can tell me whether you understood it the same way. Ordinarily, unsupervised learning is based on correlations in the data space, basically. What correlates and covaries with what? And on the basis of that information, and of course you added to that that information shouldn't be unimodal, it should be multimodal, so there can be integration across, but it's still the same thing. It's basically inputs and correlations across inputs. Now what you've said is that essentially you can reconceptualize supervised learning also as correlations like that, but there's another entity in there, which is the hypothesis that's generated by the system about a given input or a given situation, and then that just produces more correlations. Now it's correlations between the multimodal input and the provisional output of the robot. First of all, do you agree with what I said, or have I misunderstood?
I think that as far as I understood, I think it's okay. Yeah.
Okay, so this, I mean, any philosopher of science would have said, well, in the end, everything, physics, chemistry, etc., it all boils down to correlations. But the spirit of unsupervised correlations is that in the unsupervised correlations, it's all just input. Whereas in the supervised one, it's a correlation between output and input. And in your case, the output, in the case of this optimization translation, the output is in fact the hypothesis, the provisional hypothesis of the system. That's what we mean by supervised. This is all in terms of formal models, but I'm a psychologist and I can say the same thing in terms of tasks, what it is that the organism or the subject does. And of course, everything is in the end based on correlation, but in what psychologists consider to be a reinforcement-free or unsupervised situation, it's just the correlation between stimuli. Whereas in the case of supervised or reinforcement learning, it's the correlation between responses and stimuli. So that's just I mean, that it doesn't take away it by saying that it's a way of optimizing unsupervised learning with hypothesis testing. It's really just saying that we have to add on the part of the agent some sort of a provisional output, and then that output can be either wrong or right. And as soon as you have a situation where an output can be wrong or right, you are spiritually in spirit in supervised learning and not unsupervised. You're basically in reinforcement learning, because if you're right, then there's one consequence, and if you're wrong, there's another consequence, and the feedback, which is the correlation, is what changes the system and makes it learn. So, all right, that's not exactly a question, but it's a yeah. Go ahead.
Yes. I think that you're taking a good point, and yes. So I mentioned a bit about predictive coding. So that's that idea is very much same as what you said, I think.
Yeah.
So
by definition, predictive is in the reinforcement context, because your prediction can be either correct or incorrect. It's true that if you set up the model, then the way that the system learns that the prediction was correct or incorrect is through correlations, which you can think of again as being unsupervised, but it's not unsupervised. As soon as there's an element of you do something and there are consequences, you're in the domain of what psychologists at least consider to be supervised learning, reinforcement learning, and not unsupervised learning, which is passive correlation.
Yes, yes. Maybe that's not a question, but a comment.
Yes, yes. But in supervised, in reinforcement learning, the correlation is not known beforehand. You know, whether the outcome will be positive or negative, or is not known, and what the consequence will be is not known either. So I think that that's why reinforcement learning is much stronger than supervised learning, because you really do learn from it. In supervised learning, basically you're trying to reach a goal that you've already established, and then you're trying to set up your system in such a way that it behaves according to your wishes. In reinforcement, I think there is free will, if you want.
Yeah, but the contest here, Munir, the contest is not between supervised learning and reinforcement learning. For our purposes, reinforcement learning is just a form of supervised learning. The usual form, it's pre-coded, and in the predictive form, it's not pre-coded, it's trial by trial learned from the environment. But the real contest is between unsupervised learning and supervised learning, of which reinforcement learning is a particular case.
We could have discussion over this.
Yeah, Tadahiro, it's your show.
Yes, actually, maybe I had a similar discussion with you 5 years ago, but the very confusing point or important point is to distinguish, how say, the psychological or say the practical psychological distinction between the supervised, unsupervised, and the reinforcement learning, and mathematical, the formulation of the unsupervised learning and the supervised learning and the reinforcement learning. Actually, what I suggested showed here is that this is a kind of mathematical viewpoint. Actually, from the mathematical viewpoint, they can be united, and actually the reinforcement learning, some algorithms of reinforcement learning is become exactly same as the probabilistic modeling and inference. That can be called, may be able to be called the unsupervised learning. So when we have the discussion, we should distinguish the kind of phenomena of the unsupervised, the kind of story told in psychology text. This is the reinforcement learning of rat or something, and kind of the mathematics of the reinforcement learning and the unsupervised learning. Can I explain? Yeah,
I agree completely, and
yeah.
in fact, that's what I meant when I said there's the model and then there's the task. And I think Munir can agree with this as well, because he emphasized the prediction. Prediction in real time is a task variable. It's not a model variable. It's and that's why Munir said that if it's known or it's not known in advance. If you put time into it and you think of a learner who's traveling in time and getting better by learning something in time, at some point there's something that the learner doesn't know. And if it's about supervised learning, it's not just about correlations that the learner already has, but about correlation between what the learner has, what the learner is inclined to do, the prediction the learner makes, and the consequence, which is outside. I mean, the consequence is not. That's another reason why the usual form of supervised learning is kind of canned canned time. What it does is you put in advance all of the possible outcomes and you pre-train the system.
That's right.
If you do this, then this, so on. Whereas in reinforcement learning, you unpack it in real time.
That's right.
But the fundamental difference is what Munir said, which is that one is a prediction, and it depends on an outcome to see whether the prediction is correct or not, right? And that's fundamentally reinforcement learning. No matter how, I agree with you're absolutely right that you can formally make the model such a way. If you ignore the fact that time is happening in real time, you just build that into and you add in the correlations between the current state and the outcome state. You add that into the model, but and not unpack it in time, but simply put it in the model, then it all looks the same. It looks like it's all correlation. But that's why I said physics and chemistry is like that too. Everything is just correlation.
Thank you.
Munir, did I misrepresent?
No, you're okay. In fact, the way I see it is supervised learning for me is a static process. Basically, you have the game laid out beforehand.
Yeah.
Okay, so that there is no real intelligence there. It's more pattern recognition.
You're right, but that's a model feature. Right? Yeah. It's not a task feature. In task, you can't do supervised learning with as a task. You can't shove it into a learning subject all of the options and all of the consequences. It has to unfurl in real time.
Yeah, but I don't know whether I got the presenter's hypothesis right, but apparently in his case, basically he seems to replace those goals or outputs in supervised learning by some kind of latent variables or innate outputs. And if that's the case, then I don't know whether that correlates with actual biological evidence.
Tadahiro?
Biological evidence?
Yeah. Because apparently what you're saying is there is some kind of built-in capabilities or goals or aims that guide the system in its behavior. And then it adapts the environments to that. The environment, the sensory motors information that surrounds it based on that. I think you had this slide at the beginning that kind of said that, where you were talking about latent variables. And I was just curious as to whether there is a biological correlate to that. That is, to have evidence that in the brain we have such behavior.
Okay.
I know in linguistic theory, people like
Chomsky, yeah,
had this hypothesis that there are
universal grammar.
Yeah.
Okay, yeah. So basically, from the viewpoint of biological basis, I'm still a bit naive, actually. So, but for example, so I'm very much. Let me show you the.
By the way, this is a beautiful picture.
So actually I respected the Japanese neuroscientist Kenji Doer. He is leading the big project in Japan now. But about 20 years ago, he hypothesized that the cerebral cortex is conducting the unsupervised learning, and basal ganglia. This is widely known that the basal ganglia is conducting reinforcement learning, and the cerebrum is conducting a supervised learning for internal modeling. So actually the cerebral cortex has a very uniform structure all over the cerebral cortex. Then I very much inspired by this idea, and my ambition is to creating the create the model or the unsupervised learning architecture, the representing the how to say the conducting the most of the tasks, most of the functions of the cerebral cortex. That's my kind of naive the motivation, and also the predictive coding and the free energy principle. Such kind of very similar idea was how to say proposed and discussed in the neuroscience community. That is another inspiration that I got.
Okay.
Pierre, did you have another point? Where you go? Looks like Pierre disappeared. Other questions or comments? Mo, I can't believe you have nothing to say.
Well, I had a question, but it was a bit tangential because the presentation was extraordinary and very well covered. But it had to do with machine translation, which you showed initially. I was wondering if, because what you're doing essentially, this anchoring is has some social relevance. For instance, what qualifies as a kitchen does not qualify as a kitchen for every culture. Similarly, affordances related to any given object is not the same. So there's definitely this intrinsic social embedding. And so I was wondering if your machine translation was able to take that sort of, well, I mean, I don't know that you're using it, but you mentioned it. If it was possible to do a sort of value-laden machine translation type of effect on your machine so that changing context would intrinsically be translated.
Yes. That's a very interesting point and a good point. So basically what I mentioned in the explanation of the machine translation. So that was just an example of the current AI technology. So my study is not about machine translation, but of course in the current machine translation, basically all how to say everything is conducted on just text, usually. So that they don't know, for example, what kitchen means, and they how to say from the viewpoint of a simple programming problem written by Harnett, and this is a kind of just treated how to say text word-to-word relationships. So syntactic meaning that can be given from the corpus data. But the machine translation system don't know what kind of visual information the kitchen have, what kind of actual shape of the kitchen is, and so on. So and actually the visual information of the kitchen depends on the country. Of course, my kitchen in Japan is different from what the kitchen in UK or France or Canada, and I don't know. So, and such kind of cultural dependency should be affects our concept of kitchen or everything, every other notion concept. So I think that treating such kind of cultural dependency or such kind of differences that we need to think about. We need to treat not only text data, but also other physical and social experiences. And based on such kind of information, we should we should construct a kind of computational model and have a discussion over such kind of differences. So actually, I haven't conducted such kind of research, but for future research, I think such kind of point is very important, I think. Is it okay?
Thank you.
Tell me if this is a fair simplification of what you just said.
Sorry.
No, let me I'm going to say something that I think is what you said, but I'm going to say it more simply, but I may be wrong. Your intuition is guided by this multimodal notion.
Mm-hmm.
And what you're saying is the text processing is just text.
Yeah.
If you want to fix this kind of thing, you have to make it more multimodal. You have to introduce the sensorimotor data for
mm-hmm.
each of these different cultures.
Mm-hmm.
Is that what you mean?
Yeah, basically. Yeah.
Okay. But yeah, but that doesn't settle the issue about supervised, reinforcement and unsupervised. Pierre, you came back. Go ahead.
Yes, my connection was cut off. To me, the real question is about the motivation of learning. This is never addressed in there. And for the biological machines,
you have sound problems, Pierre.
This motivation is coming from. That's why I was cut off before. Sorry. Is it better?
Yes, it's good now.
Not really.
Yeah, now it's good. Go ahead.
Okay. For biological machines and humans, or the motivation comes.
Pierre, it's still cutting out, and this is a good discipline. Pierre, wait a minute. It's still cutting out. So what I suggest is when it starts working, formulate what you want to say.
My connection not stable, so.
Yeah. And I think I can predict the Pierre's question.
Okay, go ahead.
Maybe the motivation of the learning and the biological system has a kind of.
Yes.
Has the basis of the motivation, and what does drive my system, so something like that. So basically, let me revisit this slide. Can you see my slide?
Yes.
Yes. So actually, our approach is very much biased to the unsupervised learning. The unsupervised learning is a kind of predictive coding. So what they want to do is the modeling the world. So reducing the uncertainty. We want to make everything predictable. That's the kind of motivation of my system. So this is very much different from the motivation for survival, or something like that, but very innate one. So I think to my understanding, our biological system, especially the human, the brain has many types of many types of the source of motivation. So actually I don't know much about. I'm not a professional neuroscientist, brain scientist, but the reinforcement learning, basic ganglia, is provided with the reinforcement signals, from other part. Such types of motivation, basically for survival. Such kind of motivation is not modeled basically in our system. So basically what our system is caring about is predictability and modeling the world prediction. So of course, as a biological system, the other part or other motivation should be integrated. And actually, my collaborators are very much interested in such kind of topic. But yeah, that's our future work and also current work as well.
Very good. One last question from Mao, and then I will thank you.
Yes. So you're mentioning that the motivation for your, one of the possible motivations for your machine is epistemic value, and arguably minimizing surprisal is the way that biological systems survive. So in the same way, epistemic value. So, and looking at your model, it looks like it's basically inferring states. So I was just wondering, how different is the generative model you've built from active inference?
Active inference. Yeah, yes. So the active inference, is a way of, is the idea of basically action selection that can involve the inference of latent variable as well. But Carl Friston and that's the studies of active inference that assume that the action selection is also the part of inference. And that's based on the probabilistic generative model kind of view. So we share the basic concept, I think. And actually, recently, I honorably wrote such kind of a paper with Carl Friston as well. And yeah. So I love such kind of idea. And maybe so the active inference, the discussion about active inference can be implemented on our model as well.
Very good. It is now 1:30 in the morning in Kyoto. And we think we should allow Professor Taniguchi to have a little bit of sleep. But before that, I want to thank you very much for a very stimulating and informative presentation. By the way, your colleague Tan Juni is going to
Juntani?
Yeah,
Juntani, he is my friend.
He's speaking next week.
Yeah. His lecture is always very interesting, and he is very much fan of predictive coding. Yes. So maybe you will know that you will listen to the many things about that. And please, find some similarity between my talk and Juntani's talk. Methodology are very different. He using a recurrent neural network, and I'm using a graphical model, generative model. But I think we share many things. Yeah.
Very good. And thank you very much. Well-earned night's sleep.
Thank you very much.
Bye-bye, everybody.
Thank you. Thank you very much.